Okay, so this week for the homework, I want to do something a little bit different since most of you will be doing the exam. So what I would like to do is, instead of giving you any written homework problems that we'll be doing the next 2-week window, what I want to do is give you some papers to read on the circle method. I want you to talk with each other in groups about these papers, and then give some kind of 5, 10, 15-minute presentation. Okay? This is really what grad school is like. Grad school is all about your advisor piling papers up on you and continuing to pile papers up on you until at some point they have to leave for a meeting, pick up their kids, something like that. This has happened to me multiple times. And you are expected to learn the papers. So what I will do is I will give you one of the original papers by Hardy and Littlewood on the circle method, just so you can get a sense of what the subject looked like initially. And I'll give you maybe 1 or 2 of the more recent papers on the circle method. Now what this means is you should not be able to present all the technical calculations. But this is the way graduate seminars work, is you are given papers of interest, and the goal is to read the papers and get an idea of what's going on, what can you mine from them, and then what additional problems could you maybe apply them to. So this will be like a 2-week assignment. Have 2 weeks. However many of you want to be in a group, if you all want to be in the same group, that is absolutely fine. When I was in graduate school, there was the secret Sonic student seminar list, which really wasn't that secret because it was a huge part of the department. And just a huge number of us just met frequently to go over papers. This is how you learn. And so this is a graduate class. By all means, if you all want to be in the same group, that's fine. And then if the problems in the papers I send you don't seem that interesting, let me know and I'll find you something else. It doesn't have to be from the circle method section. I just thought that this would be a good method to choose, both because it's very old, it goes back over 100 years essentially, and 2, almost 100 years, and 2, there's been a lot of progress on it recently in terms of technical mastery. And this is where the subject becomes very difficult. When a subject is old, it's hard to do better than the other people. Right? The greats have already walked the earth, they've already mined the easy things possible from this. If you're going to beat them, you've got to somehow find something that they missed. You have to use more techniques, you have to combine new things, you have to take advantage of other results in other fields. Or you have to be lucky and you have to see a simplification, an algebraic approach that was missed. And so I thought it would be a little bit interesting to see, one of the papers I'll give you is the completion of the proof of the ternary Goldbach problem, that every large odd number, and now large means 7, can be written as the sum of 3 primes. Okay, so right now we're back to the circle method. So circle method. And then we have not done generating functions in great detail in this class, right? We have not done the Fibonacci numbers and their generating function. Correct?
Homework problem on it, but
we had a homework problem, but not writing down the generating function of the Fibonacci's. Okay, so what I want to do is there a dispute? Have we done the Fibonacci generating function in this class? Okay. So what I want to do is I want to talk a little bit about how the circle method works. We've talked a little bit about why generating functions are useful for the circle method, how we can write it down as an integral. I want to talk a little bit about how we would understand that integral, and then I'll segue back to the Fibonacci numbers and do the generating function of the Fibonacci numbers, just so you can get a sense of how good life can be. Okay? Then we will return to analytic number theory about writing numbers as the sum of primes or powers and whatnot, and you'll see how miserable life can be. All right. In principle, it's a very similar calculation. The difference between the Fibonacci's and what's going to happen here is a closed form expression. When you have a closed form expression, not surprisingly, there is a lot you can do with it. When you do not have a closed form expression, the subject becomes quite painful in terms of how well the calculations can be done. All right, so for example, if we have fn of x is the sum p less than equal to x, we'll do log p times e to the px. And here, e to the z is going to be e to the 2 pi I z. This is very common notation to write it like this. Part of this, I think, goes back to the older days before tech, when you were doing things in old processing environments. But we'll write something like this to mean e to the 2 pi I px. So our functions are going to live from 0 to 1. If we look at fn of x cubed, e to the negative nx dx and we integrate this from 0 to 1, this is going to be R3n of n. The number of ways where you can write n as p1 plus p2 plus p3. Do I need to worry about the fact that these primes are at most n? There is a mistake in what I wrote. Is the mistake that I have to add the restriction that the primes are at most n? So when we expand this out, we'll get things like the sum of log p1, log p2, log p3, e to the p1 plus p2 plus p3 minus n times x. But where do my primes live? My primes, oh sorry, that shouldn't be an x, that should be an n, sorry. My primes are at most n. Do I need to remember over here that I'm writing n as the sum of primes at most n? Or why don't I need to worry about that? Yeah, if a prime is greater than n, I'm not going to be able to write n as a sum of primes involving something greater than n. I can drop the condition that the primes are at most n if I'm evaluating this number at n. What if I evaluate this at 2n, or 2n plus 2? Then I might be able to get it with primes at most n, but if I can't, that's fine. Maybe I have to use just a large prime to do it. But at this special point, that's fine. What about when I say the number of ways of writing n? Is that correct? Because I'm waiting. So it's the number of ways weighted, right? So I have a takeaway that I post on my webpage from all the different classes. I'd like you to help me modify the one for advanced analysis. One of the takeaways of this class is it's easier if mildly discriminate. So log p weights are great. Log p weights are wonderful. If the weights vary wildly, then you're in trouble. But if the weights are almost constant, then there's not that much of a difference between things. And we've seen a little bit of evidence that the primes are much nicer if you use a logarithm. Why? Why do we want to use logarithms? Why do we want logarithms for primes? Was the homecoming loss this bad that everyone is still in shock? Where did the logarithms from the primes come from?
The von Mangold function.
Well, they come from the von Mangold function, but why do we have the von Mangold function? Why is this arising? I left it in my office. I almost brought it down. I bought a bell. Well, I actually didn't buy a bell. I got 2 bells for free this weekend.
Oh, because we took a logarithm.
Because we took a logarithm of the Euler product of the zeta function. That's always lurking in the background, right? This is from the Euler product and the log derivative and contour integration. That's what's really going on here. That's why we want to discriminate among primes like this. Because if we put in these log weights, we can use these tools from complex analysis. And these tools from complex analysis will make things a lot easier to study. All right. We need to understand this function fn of x. Anybody have a choice of x? I will accept any smartass response. 0, right? This is the best chance. Fn of 0 is the sum p less equal to n of log of p times e to the 0. Well, if it's just e to the 0, e to the 0 is always 1. So this is going to be the sum of all the primes less equal to n of log of p, which is going to be approximately n. If I was counting the primes up to n, it would be n over log n. Since each one is weighted by log n and they're all about the same size, it's not surprising that this sum is about of size log n. If you want, I could truncate and I could look at the sum p less equal to n to the 1 minus epsilon log of p plus the sum of n to the 1 minus epsilon less than equal to p less than equal to n of log p. What's the maximum contribution I could have in this region? How much could that be? Worst case scenario, largest it could be.
N times log n, or n to the 1 minus epsilon times log n to the 1 minus epsilon.
Right, and I can even be careless and I'll just even call it log n. Because if I raised n to the 1 minus epsilon here, that's going to just affect the constant outside. I'll put it here so it's... And then this is going to be less than or equal to the log of n over n to the epsilon times n. What can you say about this quantity here? Log of n over n to the epsilon. Yeah, this is going to go to 0. So the primes before n to the 1 minus epsilon really contribute a negligible amount. And then in this range over here, what am I going to get? Well, it's essentially the number of primes up to n minus the number of primes up to n to the 1 minus epsilon. And they all have essentially the same weight. So it's going to go from, log of n to the 1 minus epsilon times the number of primes up to n minus the number of primes up to n to the 1 minus epsilon to log of n times the number of primes up to n minus the number of primes up to n 1 minus epsilon. And now if we use the prime number theorem here, this is n over log n, n over log n. This is n to the 1 minus epsilon. So this is a lower order term than this. So the log n's come through. And we can see that the value of this sum, by the prime number theorem, it's almost n. We've just shown it's between 1 minus epsilon times n and n. That's pretty close. We could do a little bit better. Instead of splitting it at n to the 1 minus epsilon, where might you want to split it? Can we do a better job splitting than this?
N over log n.
So n over log n, and so you're almost thinking like a number theorist.
N over log n.
Almost. I think you went a little bit too far.
Log.
Not quite. See, what you're trying to do is you're trying to solve a specific problem ahead of time. You always want to give yourself a free parameter. Yeah, have free parameters. So again, I can trust you to read the book. You can go through the tedious calculations. Then you can close the book in frustration, and then you can open it up again later and go through the tedious calculations again. There's a lot of algebra that needs to be done for this, a lot of bookkeeping, a lot of special values of arithmetic functions. I don't want to concentrate on that. You don't want me to concentrate on that. I want to try to concentrate on big picture stuff. When you try to say ahead of time, I'm going to do log of n, or log squared of n, or log n, you give yourself no freedom. When you do the calculation, you've fixed what you're going to be doing. You want to allow yourself a little bit of an option so that as you see how the calculation is going, you know what to do. Notice I didn't do n to the 1/2. I didn't do n to the 3/4. I did n to the 1 minus epsilon to give myself a little bit extra freedom. So we could try the sum p less than or equal to n divided by the log of n to the alpha of log p versus the sum n over log n to the alpha less than or equal to p less than or equal to n. So now if we do something like this, this is going to be less than or equal to the number of primes up to here. So it'll be, pi of n over log n to the alpha times the largest value would be the log of n over log n to the alpha. Well, this is log n minus log log. The minus log log is small relative to the log. So this term really looks like a log of n. This is going to look like n over log n to the alpha. So this is going to look like n, oh, it is before, n over log of n to the alpha minus 1. And if we're trying to show that it's smaller than this, what do we need to choose for alpha?
Absolute value greater than 1.
Correct, but no absolute value.
Just 1 point.
Right, we're not going to take a negative alpha, okay? So we're okay if alpha is greater than 1. So if alpha is greater than 1, this term is going to be much smaller than n. And by much smaller, I mean you're going to win by a couple of logarithms. This is not a huge amount to be winning by. So a lot of these methods are extremely delicate, and the goal is to just barely get more logarithms in the main term than the other term. Okay? And so the question is, how refined can we do the analysis? Let's look at what's going on over here. What can we say about this sum? Well, this is going to be less than or equal to the log of n over log of n to the alpha times pi of n over log n to the alpha minus pi of, oh, so this is the pi of n, and the next one is pi of n over log of n to the alpha. So that's going to be the lower bound. Well, if we look at this, this will be log n minus log log. The log log will be negligible. This will be n over log n, and this will be n over at least log squared. So this will be over here. Actually, if this is a lower bound, sorry, it's going to be greater than or equal to. So this will be essentially greater than or equal to n plus small. And that's a little bit better than what we had before. So this is how you try to do estimations of this type. Give yourself a free parameter, see where you need to go. So if we had tried taking alpha equals 1, we would have just barely lost. If we tried alpha equals 2, we would have won, but with maybe a little bit more than we need. And so the goal is we want to try to get estimates. We want to try to estimate how big is something. How much cancellation do we have? Not surprisingly, the better cancellation you have, the harder it's going to be to get that. So you want to get a sense of what is the weakest possible result we can get. Now this is not quite the same, but morally it's similar. It's I have an integral, I have a sum, I'm trying to get a sense of what is its magnitude. Where is the contribution coming from? Most of the contribution is coming from the primes very close to n. If we move a small amount away, it's actually a negligible amount of the interval. And so here, even just moving a little bit more than log n away, it's now negligible. All right. So returning to what we were doing before, let's look at this function, and let's try to get a sense of its size. So we got that fn of 0 is about of size n. So we know fn of 0 is about n. What is the next point we should try to understand this function? And if you're too much of a smartass, I will reject it. What would be the next natural point to try? You can say it, and I'll just say no. What value of x would you like to choose next? I won't let you, but what value would you like to choose? 1. I'm not going to let you choose 1. Why am I not going to let you choose 1? It's the same thing. Is also fn of 1 by periodicity. Right? The function's periodic. I'm not going to let you do that. All right. Where do we go next? A half, right? Halfway between the two good points, the simplest rational number. So what is Fn of a half? So Fn of a half is going to be the sum p less than or equal to n log of p, and I'll write it out, e to the 2 pi I p times 1/2. The 2 and the 1/2 cancels, and we have e to the pi I p. So what can you say about that? So what do we know about e to the pi I p? If I take p equals 2, it's 1. Okay, after 2, it's never 1. And what is the value after 2? Negative 1. So this is equal to negative 1 plus, well, actually negative, I guess, log 2. And now you can understand for the heuristics why we don't want the logs. And now what we really have left is plus, sorry, this is a plus 1 there. Then we'll have a minus 1 here, because all the other ones will be negative, minus a sum 2 less than p less than or equal to n of log of p. So essentially, what is this sum? N, right? Technically, it's a little bit less. It's n minus the log of 2. Right? And we have a log of 2 over here. So technically, we get like 2 log 2 minus n plus small. And the more we know about the distribution of primes, the better we can do. And why do we have this extra log 2? The problem is we're missing the prime 2. Missing prime 2. So sum isn't approximately n, is approximately n minus the log of 2.
Why did we take it out, or is it in the small now?
Which, over here?
Yeah. I mean, why do we take out the log 2?
Well, just because when we look at e to the pi I p, if p is 2, we get e to the 2 pi I. E to the 2 pi I is 1. So when the prime is 2, we get the exponential function is 1. At every other prime is odd. For the most part, I hate the comments, there's only one even prime. Isn't that fascinating? Yes, and there's only one prime congruent to 0 mod 3, and there's only one prime congruent to 0 mod 5. But the splitting into evens and odds is useful here. If you put in any odd prime, what is e to the pi I p? It's always negative 1.
Yeah.
So then this sum over here breaks up into the log of 2, and then every other piece is going to be a negative 1 times the log of p. If you wanted to, we could easily include we can include these log 2's into the small.
Okay.
I just know that I'm writing them down. You're absolutely right that we could put them in the small. Okay. The main thing is that this is of size negative n. So the function goes from size n to size negative n, essentially, and then back up to size n. So I feel like the Karate Kid, okay? It goes up and down fairly often. Where would you like to try it next? A quarter, and after that? I'm sorry? No, not an eighth, not a 16th. No, after a quarter, 3/4. Right. And after 3/4. No, I'm serious, because you guys are discriminating. You've left out a third. You went from a half to a quarter. I mean, what about 1/3? 1/3 would be nice, 2/3. So you look at rational numbers, a over b. So the next thing is to say, well, what would happen if we tried to look at this at rationals of the form a over q? I can't use p for my rational denominator because I don't necessarily know I'm evaluating it at a prime. And of course, I want to preserve the letter p for the primes that are defining this function. So let's study Fn at a over q. So Fn at a over q is going to be the sum p less than or equal to n we get the log p weights. And now we have e to the 2 pi I PA over Q. Right? This is now a sum from hell. Right? How do we evaluate this? We need to know where the primes are. We do not really know too much about where the primes are. We have some ways to count them, but we don't want to have to resort to knowing too much about their exact location. The idea is, however, that we don't need to know exactly where they are. This function only weakly depends on the prime. So let's say Q equals 5. Can you give me two primes that have the same contribution?
Q and 7.
2 and 7 contribute equally. Excellent. So why do 2 and 7 contribute equally? They're congruent to 2 mod 5. When you look at this, I have e to the 2 pi I PA over Q. All I care about is P divided by Q. And so we can rewrite the sum as the sum over all values of R mod Q, the log of P, let's do this carefully. We'll do it this way. The sum over all R modulo Q, the sum over all P congruent to R modulo Q, log of P, e to the 2 pi I. Now what should I write for P? I've got PA divided by Q. That's what the function is. But I don't want to write P here. What should I write here? R. And we write R because P is congruent to R mod Q, so we can replace this. As P is congruent to R mod Q, replace P with R. What's nice about this quantity now? We don't need to know where the primes are. What can we do to this quantity?
Take the integral from 0 to 1.
I'm sorry?
Take the integral from 0 to 1.
It's not a bad idea to convert sums to integrals, but this is not a problem where we can convert sums to integrals. What should I do with this piece? I've got a sum over R, sum over P, log P, e to the 2 pi I R A Q. Pull it out of the sum. Does this have any P dependence? No P dependence. Pull it out. Right? We can pull it out of the sum. So this is now going to be the sum over all R modulo Q, e to the 2 pi I A R divided by Q, the sum P congruent to R modulo Q log P. Does this look familiar? What is this equal to?
R over Q.
What does it look like? What problem does this look similar to? Prime's an arithmetic progression with log weights. That's exactly what we want to know. This is just asking us how many weighted primes are there congruent to R mod Q? What would be the easiest value of Q to look at?
2.
1, right? Easiest value of Q is 1. I want primes congruent to R mod 1. Okay, that's primes. Then your 2, 3, 4. The smaller the Q is, the easier it's going to be, the fewer congruence classes there are, the fewer residue classes there are. As Q increases, this gets harder. Are all R equally good?
First order.
To first order, every R is equally good? I'm sorry?
1, 0. Relatively.
Relatively prime, right? If there's some r's that share common factors with q, how many primes could you have?
1.
At most 1, right? If r happens to be prime, maybe you can get 1 lucky prime. So when I look at this sum, we could actually restrict it to r and q are relatively prime with a negligible cost. So we can put in over here rq equals 1 plus small. Because the contribution from the primes that are congruent to q is going to be small. What is that small going to depend on?
N.
So it'll depend on n. Anything else?
Q.
Q, excellent. So you often want to put in, in your notation. So if q is really small, the worst case scenario I have is if every integer up to q is relatively prime to q. Okay, that's not going to happen really once q is modest. But you could have a positive percent of numbers that are relatively prime to, that share a factor with q maybe. Maybe q is even and you get all the evens coming in. So this is going to be of size maybe q log n. Does that seem like a reasonable bound?
Log n at most. Log n representing at most the contribution from each.
Right, each one is going to contribute at most log p, p is at most n, I have at most q of them. The contribution is going to be of size q log n. If q is small relative to n, remember, when we took x to be 0, when we took x to be 1/2, we were getting contributions on the order of n. These little bitty terms of size q log n, right? Q log n is negligible when q is small relative to n.
I thought we said the worst case was when q was small.
Well, I'm saying the worst case is when we have a lot. I'm just saying right now the contribution from the r's that share a factor with q. Worst case, each one contributes a log n, and worst case, there's q of them. And so the worst possibility for this is q log n. If q is much smaller than n, then we'll be fine. So the idea is if we are looking at rationals with small denominators, we don't really have to worry about that. These sums actually have a really nice value. The difficulty then comes down to here, counting primes in arithmetic progression with log p weights. Fortunately, we just did a unit talking about how you would do something like this. So if you want to make progress in the theory, you need to have really good estimates for something like this. This is the difference between Goldbach type problems and Waring type problems. It's what kind of inputs do you need. We need really good estimates. So to first order, this is going to be 1 over phi of q times the sum of these, which will be n. It's essentially saying that to first order, the primes fall evenly among the different congruence classes, plus lower order. And here is the problem. We do not have good lower order estimates of this. We cannot let q get very, very large. We would love to take q to be n to the 1 minus epsilon. No. We would love to take q to be n to the epsilon. No. Can't even take q to be a power. What we can do is we can take q to be a couple of logarithms of n. We're okay if q is about, say, log n to some power. And then in the circle method, you have this game of chasing constants. Is based on how accurately you can estimate here, that's going to determine how well you can build certain arcs later on. And it's all going to propagate through and then have you figure out how large you can do things. There's the Riemann hypothesis that says all the zeros of the Riemann zeta function have real part 1/2. It turns out not only is the Riemann hypothesis true, but its generalizations are true to Dirichlet functions. We just don't have a proof yet. Okay? Once we have that proof, then we can get much better estimates here. And with these better estimates, then this propagates. And so what Hardy and Littlewood did is they actually used, I think, results towards the Riemann hypothesis. It's been a while since I've looked at their papers. I think they're called like partitio numero I'll be looking at them as I hand them out to you later this week. I want to say, they said, let's assume that the Riemann hypothesis is kind of true. And they quantified kinda to say the real part of any 0 is at most 3/4. I think that's what they needed to make significant progress. And so again, they didn't need the full strength of the Riemann hypothesis, but something non-trivial towards it was very useful. And so now this should help you following the rest of the stuff of what's going on. Notice this is going to be size n over phi of q. We then have roughly phi of q possible things here. Now these have different signs. This is an arithmetic function. And so then the question becomes, how large do you expect this to be? So we have a bunch of things of size 1. How large would you expect their sum to be? If you've taken probability with me, you must answer. Imagine they're just +1 or -1, and we have phi of q things.
The probability that it's +1 times the number of things.
Well, I've got something that's somewhat random, hopefully. Hopefully it has enough arithmetic complexity. What do you think that this should look like? How big? So I've got about phi of q objects. Some objects are +1, some objects are -1. It's a little bit more complicated because these are exponentials, but let's take the simple case. Square root phi of q, square root cancellation. So it's the philosophy of square root cancellation. If you have a sum where the terms are just randomly chosen in terms of sign, and they all have the same magnitude, you expect square root cancellation in the number of terms. Now, if things are aligning, say we have your Dirichlet characters, and we're always evaluating them at a number congruent to 1 mod q. Well, there's going to be catastrophic alignment. It's going to get very large. In general, you would expect to have lots of cancellation. So for something like this, maybe I expect this to be of size square root phi of q. I'm dividing by phi of q over here, so maybe I'm expecting something like n over square root of phi of q. Yes?
Why is it square root?
This is just the central limit theorem that if you have, if you flip a fair coin and you get, heads half the time and tails half the time, if you flip it n times, your expected value is 0. But the standard deviation is going to be like square root of the number of tosses. And so it's essentially the central limit theorem. So the central limit theorem would predict that this should be roughly of size n over square root phi of q. So coming back over here, okay, good. So this was about -n. In general, Fn of a over q should be about maybe n over phi of q to the 1/2 if q is small. Say q is about log n to some power. So the idea is the function is still quite large near rationals with small denominator. So Fn is large in absolute value near rationals with small denominator with respect to n. So whenever you do a problem, you always have to quantify what do you mean by small. Log of n to the b is going to go off to infinity. Right? It's not a small number, but it's small relative to what we're talking about. Okay. Anybody know roughly what the US national debt is?
9 trillion.
You're off by almost a factor of 2. Whether or not that's fine, that's not in my purview as a math professor. I think it's around 16 trillion. I think we've now exceeded GDP. Okay? The log of the national debt is far more reasonable. Okay? However, the way things are going, even the log of the national debt is going off to infinity, just at a much slower rate. Okay? Over here, the log is a large number, but it is minuscule relative to number n. And this is the mindset you have to adopt. What's really big, what's really small? This is going to be extremely small. Now, unfortunately, most numbers are not going to be very close to rationals with small denominators. This is how the circle method works. The idea is you break your function into points that are near rationals with small denominators and those that aren't. And near rationals with small denominators, you say my function f is approximately constant. Or better yet, rather than saying it's approximately constant, you approximate it by a function that varies very, very slowly, but is easy to integrate. And then you handle the contribution near the rationals with small denominators. And then near everything else, you show that the contribution is negligible. So what I want to do now is I want to give you a sense of how big is this function in other places. So what we want to do now is we want to look at what's going on near a generic point. Well, how can we get an idea of what's going on near a generic point? Let's look at the average value. Average value of fn. Well, the average value of fn is hard, so let's calculate the average value of fn squared. If I can understand the average value of the square, can I understand the average value? It's a heuristic lecture, so sure. Okay? So we want to calculate the integral from 0 to 1 of fn of x, absolute value squared dx. This is one of the most important techniques in mathematics. And the secret is 2 is 1 plus 1. How do you write the absolute value squared? In terms of the complex conjugate, it's fn of x bar dx. Well, if I'm putting a bar over my function, all I'm doing is I have the log of p. Well, that doesn't change if I take a complex conjugate. And then I have an e to the 2 pi I px. I take a complex conjugate, it becomes an e to the negative 2 pi I. So what I get is I get an integral from 0 to 1, the sum over p1 log p1 e to the 2 pi I p1 of x, then the sum over p2 log p2 e to the negative 2 pi, I'm starting to write out pi, I've been doing too much checking, 2 pi I p2 of x dx. And I have to use different indices of summation, so I don't confuse myself. I have an integral, I have two sums. What do I want to do? Interchange. Am I allowed to interchange? Everything is finite. I've got the Lego movie song, Everything is Awesome right now going on in my mind, except the saying finite. When it's finite, this is one of our most common techniques, switch orders. Now we have the sum over p1 less than or equal to n, the sum over p2 less than or equal to n, log p1, log p2, integral from 0 to 1, e to the 2 pi I p1 minus p2 of x dx. All right? What does this integral equal? 1 when p1 equals p2 and 0 otherwise. 1 if p1 equals p2, else 0. So now we're left with a sum, well, we might as well call them just p less than or equal to n of log p. And about how big is that? N.
Should be log p squared.
Ah, good. Should be log squared, thank you. So it should be about n log n. I'm so used to, in other times when I teach this in classes, not putting in the log p weights. But now we actually have the log p weights. So the average value of fn squared is about n log n. So in physics notation, we would write like fn of x squared average is about n log n. Therefore, just throwing the square roots around, heuristically, fn of x average value should be about n to the 1/2 square root of log of n. And again, for a lot of what we're doing, this is more than enough. This tells us that most of the time, the function fn of x has to be small. When we have a huge number of primes and we're summing these things, for a typical value of x, you're going to have massive cancellation. You've got to be very careful not to get massive cancellation. So in particular, putting in generic real numbers, you should get lots of cancellation. This is the philosophy of square root cancellation. So philosophy of square root cancellation. When I think there's only one L. Okay. So the philosophy of square root cancellation. If you have a sum of n terms that are, say, randomly distributed, then you would expect the sum to be roughly of size square root of n, maybe with a couple of log factors just in terms of just protecting yourself with growth. But order of magnitude, we expect things to be of size square root of the number of terms. What we're finding over here is that when we look at special values, we're much larger. We're of size n, or n over a couple powers of logarithm. This is why the circle method works. There are certain places where the function is large. Not only is the function large, but the function is understandable where it's large. That's important. In the places where the function is not large, we're going to try to approximate things trivially. And we're going to try to replace the integrals of f with the integrals of fn squared. So we should be making a little list of what we're going to be using or what we're using so far. And so we're using the following. 1. F squared is f times f bar. So this is 2 equals 1 plus 1. Instead of integrating f, the absolute value of f squared, what would be another good absolute value of f to integrate? What power? If I couldn't do f squared, 4. If I can't do 4. See, now we have a difference. Is it 6 or is it 8?
Because then we can group it into twos. Maybe split it into 2 groups of 4 and then split those into 2s.
Well, if we have 6, can we split it into groups as well?
We have.
It turns out powers of 2 are better for a lot of things. Powers of 2 are often nice.
We usually get cancellation.
Yep.
If there were 6, there would be nothing to cancel.
It's more subtle than that, but powers of 2 are often very nice. At the very least, you want pairings. The point is, we don't want the absolute value of f cubed. That's bad. But to the second, to the fourth, to the sixth, there's a hope of pairing things off. So that was the first thing. Next is integral of sum is sum of integral, and exploit a full quantity. We need to somehow exploit some kind of cancellation. We need to switch orders and somehow bring ourselves to a point where we have a nice integral where we go over everything and then it's going to cancel. These sums are just a nightmare. And this gives us the average size. And now this is giving us average size in terms of the average value of fn squared. But we're going to really be wanting to look at like the integral of the function, the integral of the absolute value of f. What could we use to try to get an understanding of the integral of the absolute value of f? So you've got to add at least one more name to that. Cauchy-Schwarz. There's a third name, a Russian who actually I think discovered it first, who's often forgotten. You can't leave off Cauchy's name. But, okay. So Cauchy-Schwarz. This is a verb. Yes. The integral of fn squared, the integral of fn times the absolute value of 1 from 0 to 1 dx. This is less than or equal to the integral from 0 to 1 of fn squared dx to the 1/2, integral from 0 to 1 of 1 squared dx to the 1/2. This is a really nice integral. Every symbol involved is either a 0, 1, or 2. Right? We're integrating 1 squared from 0 to 1. We take the square root of that. This is just 1. So we have a finite interval. So notice how finiteness is really saving us. Because this is a finite interval, this is 1, and now we're actually bounding the L1 norm, the integral of fn, the average value, by the L2 norm. And so our statement saying, oh, let's just bring the square root inside, we can actually justify that. We can justify it by using the Cauchy-Schwarz inequality. Okay, so this is a good place to stop. I will give you some readings to do on the circle method, and then we will continue on Wednesday.